The atom spacing is about 0.5 nanometers. So 20 nanometers, you should be able to see the individual atoms.
Hello everyone, my name is Yong Wei. And before we continue with the main section of today's episode, I'd like to provide some context on what Professor Wee and I were discussing the other day. There is this superhero in the DC universe named Atom, aka Dr. Ray Palmer, which is this guy right over here. He is one of the smartest superheroes in the Justice League and an expert in nanotechnology. One of his most iconic superpowers is to have the ability to shrink and grow his body to varying degree. For example, we can see that Ray Palmer here is shrinking his body down to visit the microverse, which is this scene we're talking about. Once, Superman even recruited the Atom to help fight the threat that lies inside Batman's brain, which is right over here. The character Atom is very much related to this episode, where he has helped with the introduction on nanoscience or physics in general to readers of all ages. Professor Wee is the director of the Surface Science Lab at NUS, and his specialization is actually quite similar to the Atom, where Professor Wee often researches on material at a very small scale. Alright, with this context, let's move on with the main video. So, from our discussion, what do you think about the character Atom?
Yes, it's the most fascinating character. I hear he's a character from DC Comics that has appeared on TV, and he's able to shrink himself to the nanoscale size and see the world at that scale.
Yeah, so that type of superpower only exists in comic. What about in the real world?
Yeah, it would be great if we can have that kind of superpower in the real world. But let me tell you something. In fact, we can. So today I'm going to introduce two techniques in my lab that allows us to see things at the nanoscale.
I see. What are those techniques?
Yeah, okay. The first technique is called Scanning Tunneling Microscopy, STM, and the second is Atomic Force Microscopy. And you get images like these on the screen where you can actually see the molecule. The STM images of molecules are on the top row. Essentially, STM works by having an atomically sharp tip like this. Imagine there's one atom at the end, approaching the surface, so close to the surface that you have a small tunneling current flowing between the tip and the surface. And if you scan the tip across the surface, the tip will follow the electronic shape of the molecule, and hence you get the image on the top row.
Okay, what about the AFM images? Are they the images on the second row?
Yes, the AFM images are the images on the second row. This time we measure the forces. That's what I call atomic force microscopy. And the forces are very small, but again, if you scan the tip across the surface, this tip feels the forces and hence it follows the shape of the molecule, and you get the second row of images.
If we want to summarize the difference between AFM and STM, what are the main differences between these two techniques?
Yes, the STM senses current, a tunneling current between the tip and the surface. AFM senses force. So it measures the force between the tip and the surface. These are the main differences.
Okay, sir, so are we able to view the STM and AFM techniques in NUS?
Certainly, I can bring you down to my lab downstairs to see the STM and AFM instrument. Let me take you. Hi, welcome. We're in the Surface Science Lab, and this is Q+, our STM AFM system. You see a lot of stainless steel, and the reason is because it is in ultra high vacuum, which is 13 orders of magnitude below atmospheric pressure. It's like outer space. So everything inside this chamber is in a really very high vacuum. And this lab is on the ground floor because in order to image a single molecule, you have to get rid of all vibrations. So the whole system is mounted on some spongy material, and inside, the STM is mounted on a stage which hangs on springs so that the STM AFM is essentially isolated from the environment. And here you see there are pumping systems all below the table here. These pumps basically bring the vacuum down from atmospheric pressure to ultra-high vacuum.
Why do we need ultra-high vacuum?
We need ultra-high vacuum for two reasons. The first reason is we want the surface to be atomically clean. We don't want any water or gas molecules like oxygen, nitrogen, carbon dioxide to stick on the surface. That's why it has to be very clean. Also, some of the techniques we use require a vacuum environment.
I see. So I noticed that there are a few like aluminum foil on the machine. What are those?
Yes. In order to achieve ultra-high vacuum, which is about 10 to the minus 10 millibar, we have to pump this whole system in 3 stages. And in addition to that, we have to bake the entire system. It's just like putting the whole system in an oven. And we can actually cover this whole system with shields and heat it up to 150 degrees centigrade. The reason we do this is to accelerate the degassing of molecules out from the whole system so that when we turn off the oven, it will cool down and reach ultra-high vacuum. And sometimes we just want to heat up certain parts of the system, and that's why we use this kitchen foil that you find in your kitchen.
So they are just normal aluminum foil?
Yeah, it's normal aluminum foil. This is the tip we use for STM and AFM experiments.
Yep.
The tip is you can see where the arrow is. It is glued onto a tuning fork which looks like this. A tuning fork makes a sound at a very fixed frequency, and you can find such tuning forks in quartz watches. So this tip basically is the tip that does all the work you have. In this AFM mode, besides scanning the force, we actually apply the natural frequency of the tuning fork. So the tip is actually vibrating, and this increases the sensitivity when it's scanned.
Yeah.
But it's an STM image, which is an electronic image, but it's not very clearly resolved. And in the AFM technique that we use with the CO molecule, you can actually see very clearly the bonds, as it were, of this molecule.
Yeah. So in terms of resolution, STM will always be not as clear.
Well, in the past, STM gives better resolution than AFM. But just a few years ago, another IBM group in Switzerland invented this technique of sharpening the AFM tip with a CO molecule. So now, if we use this technique, AFM gives better resolution than STM.
So remember that just now you mentioned that the machine can do both AFM and STM. And from what we see earlier, the image, AFM, the resolution is a lot finer than the STM. So why don't we just use AFM all the way?
Yes. This refinement of the AFM technique in recent years, or in the Q plus AFM, is much more complex than STM. Firstly, we need to get liquid helium to cool the whole system to 4 degrees Kelvin. That's very near absolute zero in order to stabilize the system. Secondly, we need to modify the tip and put a CO molecule, one single CO molecule on top of the tip, and then we scan the image. That's why it's a lot more difficult to do AFM than STM. But STM has its advantages. STM gives an electronic image because you're measuring a tunneling current. Hence, you can get all the electronic properties of the molecule. For example, whether the molecule is semiconducting, whether the molecule is superconducting, whether the molecule has specific properties that allow charge to flow in certain ways. So that's why both techniques are complementary.
Are there any type of samples that STM won't be able, or AFM won't be able to image out?
Yes. STM requires a tunneling current to flow. Hence, any insulator cannot be done by STM. But AFM can do scanning on insulators as well, since you're just measuring the force.
So what type of research or real application do scientists use on this machine?
Okay. The STM and AFM can image any material. I just showed an example of a molecule. So if you're researching different types of materials, superconductors, two-dimensional materials, and you want to understand how the materials work at the atomic scale, these are techniques you can use. For example, in the molecules we showed you, nowadays people are trying to use these molecules for electronics in a field called molecular electronics. In the future, you might see devices that work just on a few molecules. Right now, there are already organic electronic devices. For example, your OLED TV, you see molecules are already being used. So these techniques enable us to understand molecules at the single molecule level.
So does it mean that if we can achieve single molecule level, our electronic can be a lot smaller?
Yes, it does, because a molecule is about 1 nanometers in size, and this is a lot smaller than the current transistor that you use made of silicon. So if I can use a single molecule for a device, I can pack more devices on your chip. So definitely there are advantages of using single molecules.
So thank you for your time, for sharing with us your lab and STM and AFM.
You're very welcome, Yong Wei.
I hope to see you soon. Bye.
Yeah, okay, bye.